Good morning and welcome everyone to our webinar session today. So this webinar is conducted by Trident Techlabs. So today we will be talking about DO-254. Before that, let's take a look at the aircraft on your screen. When you see a cutting-edge jet like this, it's easy to marvel at the aerodynamics, the engine power, or the stealth design. But underneath that scheme lies a massive interconnected nervous system of advanced electronics. Have you ever wondered about sheer criticality of this electronics? You can see from the screen itself, each and every part in the aircraft is controlled by at least one or more electronics in that system. So if you look closely at the level across these frames, from the electronic warfare systems to the avionic equipment bay, all the way up to the flight control, like the ailerons and rudder, a single question arises. Which of these systems is most critical? Is it the system that keeps the plane in the air or on one that allows the pilot to see the dart? And as an engineer, how do we systematically decide which system carries the highest risk? Most importantly, how are we guaranteeing that a tiny glitch in the complex piece of silicon doesn't end up risking human lives? So all these questions, the answer of all these questions lies in treating safety not as an afterthought, but as an unyielding mandate. So this brings us directly to our core topic today, the Airworthiness Directive, a deep dive into DO-254 for complex electronics. So good morning, everyone. Again, my name is Vishwanta, Senior Field Application Engineer VLSI at Trident Techlabs. And over the next 45 minutes, we are going to dive deep into how requirement capture, RTL design verification, and synthesis all come together under DO-254. We'll explore how this rigorous standard provides the safety blueprint for every PLD, FPGA, and ASIC flying to do, ensuring that most critical systems are also the most reliable ones. So let's get started. So this is how our agenda looks like today. So first, we will talk about the foundation of DO-254, how the DO-254 starts, and after that, we will talk about the design assurance level, and then we will move on to briefly talk about DO-254 hardware design life cycle, and I will walk you through the planning process, hardware design process, and support process of the DO-254. And finally, I will conclude the session by talking about Siemens EDA tool in the whole of DO-254 lifecycle and how these tools can make your life easy when you're performing any DO-254 lifecycle. So the foundation of DO-254. The two kinds of hardware matters here. So simple electronic hardware and a complex electronic hardware. So these two types of electronic hardware are very important when we talk about DO-254. So when we talk about simple electronic hardwares like lighting, audio, or sensors, they can be fully verified by deterministic testing. So we always know how it will behave. But when we talk about complex electronic hardwares like FPGA, ASICs, and other PLDs, they cannot be exhaustively tested. Yet, it now runs safety critical functions like flight management, collision avoidance, or radar processing in our system. That's the crux. When you cannot test your way to full confidence, you cannot leave safety to the designer's judgment alone. So complex electronic needs a formal, verifiable mandate governing how they are designed and certified. So where did that mandate come from? So let's have a look at the origin of DO-254. That exact mandate is what we're going to talk about in today's session. So now that we have defined simple and complex electronic hardware, the next question is, why has complex hardware become such a major certification concern? The answer is shown in this slide. The thing is, its uses is increasing across modern airborne systems. Today, many aircraft functions are implemented using CEH because it gives designers flexibility, reliability, and ability to integrate more functionality into programmable devices. So this trend is visible in both civil avionics as well as military avionics. So specifically talking about in the military avionics. Nowadays, we are also on our way to develop our own indigenous military setups in avionics. So that trend has been increasing in our own domestic market itself. So in this particular way of doing or implementing complex electronic devices in civil as well as military avionics, where many processor-based applications are being replaced or complemented by FPGA, PLD-based design. When these kind of applications give us flexibilities, but it also creates challenges. So what kind of challenges it is giving is when CTH is used for more safety critical aircraft functions, a hardware design errors can have a much larger impact. Unlike simple hardware, we cannot prove correctness only by running few possible test cases because number of operating conditions is too large for such complex electronic hardware, as well as the application or the role or the criticality that they are having in the whole of a subsystem. So that is why the design and certification process must become more consistent, traceable, and verifiable. So this challenge is what led us directly to the birth of DO-254 and the need for formal design assurance guidance for airborne electronic hardware. So this is where the mandate begins in the 2005. So in 2005, the Federal Aviation Administration, FAA, of the United States of America started enforcing DO-254, which defines the design assurance guidance for airborne electronic hardware, giving complex hardwares like FPGAs and ASICs the same rigorous verifiable design assurance that DO-178B had already brought to the software. So from here, we can see that DO-254 is more like a little brother of DO-178. So it has since spread from civil aviation into military and other segments because of its sheer importance and the way it is giving more structure to the whole of a project and to the whole of the development of the subsystem or systems. So it's powerful for safety, but it also adds real-time cost risk to the design program. So then this is where most of our concern lies. So which is why getting the process right matters. So it is not just about following the guidance and finally getting the certification. So the finally getting certification itself is a risk in terms of timing, cost, and risk. So that's the reason why I'm just repeating again, getting the process right matters. So if you got the process right, you will complete your project in time so that you can put your product time in the market time. You miss something, the project is going to get delayed and everything goes delayed. So you're developing some kind of critical system here, missing those timeline matters a lot. So the guidance was later reinforced again, actually. So it started as a RTCA DO-254 in 2005 and FAA in the USA and in the European EASA have started adopting. But later on, so now we are in later after, let's say, 2 decades. Now we are in 2026, but before 2026, around 2018 and 2022, this guidance needs to be more clarified. And because of that, this guidance was later reinforced by EASA and FAA. So EASA issued AMC 2152A in 2020 and FAA followed with AC 2152A in 2022. So 22. So both of these order, both AC and AMC 2152A, keeps DO-254 at the core and add clarified objectives for custom devices, commercially off-the-shelf IPs and devices, and circuit board assemblies, extending the same assurance discipline to today's most complex hardware. So later in this session, so whatever the discussion that we're going to have, we are taking reference from RTCA DO-254, the EASA and the FAA's AC or AMC 2152A, and the Siemens Airworthiness Directive. So moving on, you can see from this picture the distinction between 178 and the DO-254. So you have an avionic LRU. So LRU stands for line replaceable unit. You have the hardware part of the programmable logic side or ASIC, PLD, ASIC, and FPGA, and you as a firmware, you have the processing part also, where you develop your applications. So BSP, RTOS, application software, maths, drivers, all this will come under the guidance or under the scope of DO-170. And the hardware part, development of hardware part of PLD, ASIC, and FPGA will come under the scope of DO-254. So we have been talking about how the DO-254 come into picture. So now we are going to talk about more critical thing. So at the very beginning of this session, you must be remembering that I asked a question. So you remember the first slide where I saw an aircraft and all the components of electronics as well as the mechanical part that is present in the aircraft. So at that time, I asked a question of how do we know that a part of electronic hardware in the whole of a subsystem is critical or not, which are more critical than others. So this slide is the answer to those issues. So each electronic components or a subsystem or systems in airborne electronic system hardware, they are assigned hardware design assurance level. So the assignment of hardware design assurance level are out of the scope for DO-254. It comes from the system safety assessment. So I will give a little bit of information about that too. But for this particular slide, in this particular table, it ranks the hardware by how bad a failure would be from level A. So level A gives is the most critical in all of the DAL level, where the failure is catastrophic, down to level E, with no safety effects, passenger entertainment systems, for example. So higher DAL level means higher criticality. So from here, we can see that the color schemes are also different here. Level A, level B, level C, level D, and level E. So I have other columns which describe each of this DAL level. And I have the target system failure rate also. So this target system failure rate data is kind of old. So I've taken it from some few research by the whole of avionic organization in the all over the world. Then we have some simple example systems also. So higher DAL means higher criticality, and that translates directly into more rigorous DO-254 process, more checks, more reviews, and more stronger evidence. So the key point is the DAL is not decided with DO-254, but it is assigned earlier during the system development and then flowed down to the hardware item. So that is how the criticality of any complex electronic hardware component present in the system or subsystem level of avionic electronic hardware is decided. So that assignment leaves on the ARP side. So the SEA ARP 4754A drives the aircraft and the system development process. And the safety assessment under ARP 4761 through functional hazard assessment, ESSA, and the resulting failure condition determines it functions down. So those level cascade down to the complex electronic hardware, and the DO-254 is simply where you deliver the assurance the assigned DAL demands. So the DAL for hardware item is established as a part of the development process. So moving on, let me just have a quick overview of the DO-254 once again. So DO-254 is design assurance standard for airborne electronic hardware. It lays out a requirement-driven process and a process-oriented way to prove the flight hardware like FPGAs and ASICs does exactly what it should. It's a mandate by FAA, EASA, and in India, it is a mandate from the Semilab, and is widely adopted across commercial aviation and industry. Now that we have understood how DO-254 come into this particular industry or particular domain of electronics, let's move on to understand more about what is inside DO-254, how the guidance gives us to do such kind of projects or process. So this particular slide, this particular chart or block diagram, let's say the flow chart, we can say flow chart also. This gives an overview of the hardware design lifecycle of DO-254. So you can see from here on the left side, we have system process. I've already talked about system process. And on the right side, we have manufacturing process. So within the dotted line is what is at the scope of DO-254, and outside that are the scopes of DO-254, are out of the scopes for DO-254. And the same particular diagram, I have taken it from the RTC DO-254 section 5.0. That is the reason why at the start of this session, I told that I will be taking reference from RTC DO-254 AC or AMC 2152A and the Semilab's Airworthiness Directive. So let's talk about each of this process briefly here, and moving on to the later slide, I will be talking more about it. So planning, there are three major processes present in this hardware design lifecycle of DO-254. Those are planning process, hardware design process, and a supporting process. So planning process produces hardware plans, and it is used by the actual hardware design life cycle and the supporting process. So 5 major processes in the design life cycles as depicted are as depicted. Its process describes its objectives and activities to reduce the probability of design and implementation error that affect safety. It is important to plan and record this process in a hardware design plan. There is a reason why planning process is very important. So even when something is changed on one process, it can affect the other processes. So each time the processes will be there, the changes should be checked to see how they impact the previous ones. So this makes all of the design process iterative actually. So there are certain items that may be produced in the life cycle itself. So that is the reason why in this diagram itself, you can see here, all of these 3 processes are interlinked or intertwined to each other. You have the planning process. From the planning process, it goes to both supporting process and the hardware process hardware design process also. So within the design process itself, we have the other processes: requirement capture, conceptual design, detailed design, implementation, and production transition. And in the supporting process, we have validation and verification process, configuration management, process assurance, and certification liaison. So we'll talk about what kind of processes is happening in each of these processes again in later slide. But in this diagram, you can see that the supporting process itself is a parallel process to all of the hardware design processes. And down there also you can see the arrows are interconnected, showing that the whole process is iterative. So anything that comes as a change during any of this process has to be iterative, goes back to planning, and it has to be reflected in each of these other processes also. So briefly talking about the hardware design process, the requirement capture will capture your requirements. The conceptual design will do the behavioral design of the requirements, implemented requirement. And in the detailed design, you will be modeling and designing the RTL net base, and the implementation, you'll be doing placement and routing, and then bit file programming. And finally, the product transition, you have to transfer your design to the manufacturing. So while doing all this, following the plan is important, and doing the supporting process of validation, verification, and configuration management is very important. So let's talk about planning process here. So the planning process is where DO-254 compliance begins actually. So its purpose is to define how functional and the airworthiness requirements get translated into actual hardware. Very important. So the requirement has to be translated to actual. So with enough documented evidence to assure the item will safely perform its intended function, it is covered in the section 4.0 through 4.2 of the RTCA DO-254. The planning process is very important in terms of DO-254. It's not just a plain documentation planning, but it is the actual document of DO-254 of the whole process that governs the whole DO-254 process. So moving on, what we have here is I'm having a planning process in a nutshell. So each processes in DO-254 has some inputs to be provided to this process something or do something, and then give some output as a end product of process. And then this output will be using as an input to the next process of it. So that is what I'm basically showing here. So what happened in planning process is you have in the planning phase, the supplier of the input will be the system engineers. System engineers will be providing DAR levels and all the system safety assessment document, and the hardware designers and a CEH designer. So the inputs are technical or functional specification to the system allocated to the complex electronic hardware, and the SSA, system safety assessment document, that defines the DAR level or and after that, during the planning process, you will be preparing the planning documents, identifying the criticality level associated to the CEH, and according to that, you have to prepare a plan. Okay, so as an output of this process, you will be having PHSE. So I have an abbreviation of what PHSE is also. So I will just abbreviate here also. So PHSE stands for Plan for Hardware Aspect of Certification. This is the main planning document or the main document that governs the whole DO-254 process. And along with the PHSE, we have other planning documents like Hardware Configuration Management Plan, the Hardware Verification and Validation Plan, Hardware Process Assurance Plan, and Hardware Design Plan. And if you want to define some standards for your further processes. You can have hardware requirement standard or design standard, verification and validation standard, configuration standards. So during this planning process itself, if tool assessment or qualification is required, that has to be performed and already provided. And as a part of verification, which is a support process, what will be happening here is all the outputs of the planning process will be reviewed by the IT and the PE and the audit by the quality assurance team. And then they will have some baseline documents. And at the end of the planning process, you will be having the first audit stage of involvement, SOI. So I'll be talking more about SOI stages of involvement in the later slides. So just a short tag, what happened in planning process is you will have input from system engineers and hardware designers, and you will prepare proper planning for which governs the whole DO-254 process. You will have all the planning documents and a standard document as a part of your planning process. And then we will have an audit, and when you pass the audit, you can move on to the next process of the DO-254, that is hardware design process. So when we talk about hardware design process, we have lots of other processes within that. So we have briefly talked about them: the requirement capture process, the conceptual design process, detailed design implementation, and product transition. Now let's talk about what happens within each of these processes. So we'll start from the requirement capture process, and you can see here is a small table. The first table we're talking about for the requirement capture process, just like I have explained in the previous slide for planning process. So during the requirement process, what happened is you develop a detailed functional requirements that are allocated to the complex electronic hardware by the designer, developing redundancy requirement based on system process. And then you also are responsible for developing behavioral specification for testing of the complex electronic hardware during this process. So what happened in short here is whatever the requirement that you have documented during your planning process, both functional, safety, and the other related requirements, you will be capturing them in the requirement capture process. All the requirements should be linked to the next level of requirement or to the next level of your design lifecycle data. We'll talk more about the lifecycle data in the later slide also. So once you do this requirement capture process, you will be getting your output in the form of document or design lifecycle data. That's what we say as an official term for DO-254. So in this whole session, I will be talking about artifacts in the lifecycle data. So artifacts are the evidence that you have reproduced as a part of your verification and validation process using tools. And the documents are the official documents that you need to show to the audit people to show that you have followed the process of DO-254 and you have perform all the processes and gather enough information in the form of the document. So that is what we are mentioning all these abbreviations here. As a part of output of your requirement capture process, you will be having hardware requirement data, HRD, hardware interface requirement data as a part of your requirement capture. And during this requirement capture, you will be doing parallelly supporting process of validation and verification also. And for that validation and verification process, you will be having hardware traceability report, high level, between the requirement documents and the hardware review and analysis report also as a part of your verification. So moving on from requirement capture to conceptual design. So the DO-254 basically follows a waterfall model. You cannot start with conceptual design and go back to requirement capture. Instead, it is more like top-to-down approach. You start with planning, move on to requirement capture, then you can move on to conceptual design. So whichever the requirement that we have captured, high-level requirement that we have captured at the requirement capture process, those has to be converted into higher-level conceptual design. So that is what is exactly happening during the conceptual design process. High-level architecture, block representation at the component level. And as a part of verification and validation supporting process, you will be already start deriving test bench architecture diagram for the complex electronic hardware that you are going to do. And as an output of this process, you will be having high-level architecture and block diagram at the CH level, and this information will be attached or will be contained in the lifecycle data, conceptual design data, CD. This is a part of lifecycle data of the DO-254. And you will also be having test bench architecture diagram, which can be handed over to the verification team. Once we are done with the conceptual design, we have to move on to the detailed design. So again, same thing in the detailed design. What we do is we convert the information, the input of the detailed design is the output from the conceptual design. So using this output as an input to the detailed design process, we'll be converting the CEH requirements, the HRD or the IRD or the CDD into lower level modules. Deriving, and as a part of supporting process, you'll be deriving test processes for the complex electronic hardware. And as an output of this process, you will be having module level schematics and the block diagrams in the form of detailed design data, lifecycle data, and in the form of ECL or RTL code synthesis netlist in that form. And as a part of your, as output for your supporting process, you will be having the hardware test plan or hardware test process. So once we are done with the detailed design, we can move on to the next stage of our DO-254, that is the implementation stage. So in the implementation stage, we'll be taking the output of detailed design data, the RTL or the analysis data at all as an input or the synthesis file as an input, and we will be performing placement and routing, defining and applying the constraints. And then finally, as a part of your output from this process, you'll be having the placement routed netlist and the bit stream. So during this whole process of requirement capture, conceptual design, detailed design, implementation, an iterative and a parallel supporting process will be going on also. The validation and verification process, configuration management, and the certification management. So we'll talk more about it in the next slide. And once we are done with the implementation and we have done the testing and all, and we have verified everything, after that only we can move on to the product transition. So what happened in product transition is now your design is verified and proven, and you have all the evidence in the form of simulation data or the linting data or any other form, the physical actual hardware testing data. So now you're sure that your design is functioning properly. Now we have to be ready for the manufacturing or the mass production. That is exactly what is happening during the production transition. Transition the hardware item for initial assembly into full-scale production using the output from the implementation and verification process. And you will be having an output of the process, consistent replication of the hardware item in production. So this is about the hardware design process. So if we remember the slide where I explained about the the design lifecycle process of the whole DO-254, we had planning process, hardware design process, and with that parallelly there was supporting process also. So let's talk about supporting process. So in the supporting process, we have validation and verification process, configuration management process, process assurance, and a certification license. So as a design and verification engineer, we are already aware of verification and validation process, but the only different thing here in DO-254, it has to be recorded and properly structured for the validation and verification process. So the validation process ensures that the derived hardware requirements are accurate and complete in relation to the system requirement assigned to the hardware. So this is more of a validation where the requirement is properly derived from it. But why? Verification process provide assurance that the hardware item implementation meets the requirement. So validation and verification goes hand to hand. But if validation, you first validate and then you also show the verification also. So there are a few methods that is usually used while we are doing DO-254 as a part of validation verification process and also accepted by the DO-254. So I have also given those methods here also. So Hessian simulation everybody is doing. But apart from that, for DO-254 code coverage is also very important as a part of analysis of validation verification process. Then we have static code linting also, static timing analysis, clock domain processing analysis, netlist simulation, and the most importantly, requirement tracing of verification and validation is the core in DO-254. So that is about validation and verification. So apart from validation and verification in supporting process, we have to, record and archive our documents, lifecycle data, and everything that is happening during the DO-254 process also. So that is where what is governed by the configuration management. That is what is meant by the configuration management. A process that is intended to provide the ability to consistently replicate the configuration item, regenerate the information if necessary, and modify the configuration item in the controlled fashion if modification is necessary. And then we have the process assurance process also. So everybody, most of the DO-254 doers usually overlook this process, but it is not most important. Why it is most important is process assurance ensures that the lifecycle process objectives are met and activities has been completed as outlined in the plan, or that deviation has been addressed. This is very important because if we are following and making sure that the planning stage document or the plan that we have been already defined are followed, then our project will be finished in time. There will be no delay in audit at all. Once we deviated from that plan, there is always a risk involved. Delay in the project, delay in the lifecycle data, ultimately leading to the delay in the reviews and audits. So that is the reason why process assurance is very important, which is often overlooked. So we'll talk about certification license in details in the next slide, which is very important when we talk about DO-254. So certification license involves engaging with the certification agency or authority. We can now understand why this is very important. So what happens is typically a designated engineering representative, also known as DER, will be communicating or will be the mediator between the certification agency and the DO-254 doer to ensure the DO-254 compliance during the development process has been done. So when we talk about certification licensing, we always talk about status of involvement. So status of involvement is nothing, but it is basically the review or audit that has happened during the whole of the DO-254 process. And officially for the DO-254, 4 official audits will be there called status of involvement. And in this table, you can see which are those 4 audits and where those 4 audits comes. So SOI 1, 2, 3, and 4 are the SOI audits that we have. So the SOI 1 will come at the end of the planning process, like I have mentioned, and it is also called the hardware planning review. So once you are passed or done with the SOI 1, then only you can move on to the next stage of requirement capture process, conceptual design process, detailed design process, and parallelly your supporting process to produce evidence, artifacts, and the lifecycle data. And you, at the end of this process, you will be having SOI 2, the hardware development review. Now the hardware development review SOI 2 has been passed, and you can move on to the next stage of implementation process. And there will be a hardware validation and a verification review or a testing review at the end of this process, SOI 3. And then finally, you will be having the final certification review, the SOI 4, where all your configuration management data, the PHAC will be checked again, including the old lifecycle data, configuration management index, and hardware accomplishment summary has to be bring out in front of this audit. Then approve everything. Once this is approved, then your design for the complex electronic hardware is certified with the DO-254. So that's the end of the story about the DO-254 process. On the left side, you can see we have the planning process, requirement, architectural, architectural design, RTL design, synthesis, question and out, and the programming, the FPGA. And then you have the SOIs here also, 1, 2, 3, and 4. So moving on, in the next slide, I'll be showing you the official hardware lifecycle data that is provided in the RTC DO-254 document. So over the years, there has been changes in the lifecycle data also. So these are lifecycle data, not artifacts actually. So we have two types of terms: hardware lifecycle data and artifact. So these hardware lifecycle data are the official document data that you have to bring out in front of the audit people. They will be checking these data and they will be validating and auditing your design and processes. And to back up these lifecycle data, you will have to have your artifacts from your whole DO-254 process of the requirement capturing, conceptual design, detailed design, implementation, and the supporting process of your validation, verification, and configuration management also. So that is where most of the role of verification validation engineer comes. So you can see here from this table itself, I have given the section in accordance with the RTC DO-254 document on the left side, the first column also. Then you have the hardware lifecycle data on the second column, and the third one is a section where the objectives of each of these lifecycle data has been defined. So I will just briefly read them out. So plan for hardware aspect of certification or PHAC, the hardware design plan, hardware verification plan, validation plan, configuration management plan, process assurance plan, requirement standards, design standards, verification standards. So all these hardware lifecycle data, I have already mapped them to each process in the previous slides, if you can remember, if we can remind. Then we have hardware requirement data, design data, detailed design data, hardware traceability data, review and analysis procedure, review and analysis results, test procedure, test results, and finally the configuration management record or configuration index, hardware process assurance record, and hardware accomplishments set. So these are lifecycle data associated with the DO-254. Now that we have understood the overview of what DO-254 is, how it comes, what are the processes associated with, and in each process, what kind of process is happening, what are the inputs, what are the outputs, and when does the reviews from the certification agency happen. Let's move on to more closer data or closer way of doing our DO-254 as RTL verification engineer closely working with the FPGA. So this is the DO-254. This is the DO-254 compliant FPGA flow. So again, you can see here from this flow itself, everything is mapped to the DO-254. So we have planning process, requirement process, conceptual design process, RTL design, synthesis, and program. We have just derived all those processes in DO-254 into a more realizable FPGA flow. So while doing all this flow, what is happening is, I'm just summarizing again, we will establish a plan, we will capture the requirements, create architecture, right, inject RTL, perform synthesis and placement routing, and finally a repeatable process and a consistent checksum to produce a big file. This flow looks simple as well as complicated, actually. Okay, it's a simple flow that we have been following, but the mandate that the DO-254 guidance is giving us to produce all the artifacts in the lifecycle data, except make it very complicated. So because of that, the verification of RT at the level of RTL, gap level timing, and hardware and its system is very, very important. So lots of verification validation is involved here. So because of that, we need to have a structured, repeatable, and assured process which can validate, manage, and test requirement, generate artifacts and documentations, manage versions and the configurations. The tools that or the environment that we are using needs to be assessed, produce good amount of evidence that this is a reliable tools that produce the correct data. And finally, it also involves performing reviews in the bucket. So DO-254 is a thoroughly planned, highly structured, repeatable, requirement-based flow which delivers a design that performs its intended function. That is a tagline for DO-254 that I'm summarizing, including all the processes. So now that we know the DO-254 compliant FPGA flow, let me just introduce you to the Siemens EDA's solution associated with the DO-254 flow, which can help you a lot in maintaining all those artifacts and all those lifecycle data, making your life easier to meet your timeline for review and finally meeting your projects or the products time to market to beat the competitions. So this slide shows that exact information here. So this is the same flow that I was showing in the previous slide. And on the right side, I have added few more extra steps also, which is very much needed when we look very closely and deeper to the DO-254 process. So let me justify all of this one by one here. So I'm not gonna repeat the process. We have already understood the process. On the right side, I will do. After the planning for the requirement capture process, you will be needing a specialized tool to capture all your requirements and maintain those traceability to finally produce a traceability report, which is the ultimate requirement for DO-254. For that, Siemens EDA is having rack tracer and live end-to-end requirement capturing tool, starting from your requirement document to your RTL design, to your verification plan, and finally to your verification result. And for your design entry of RTL and the conceptual design, Hazel Designer is the tool for that, which you can start your project, work as an IDE to map all the tools within the same environment, produce a high-level architectural representation of your design. And then once your RTL is done, the traditional flow is to go ahead with simulation and verification, but DO-254 was for more than that. It involves analysis process, actually, lots of review and analysis, your validation of what at the RTL level itself. So what happened here is on the right side, we'll move on from the right RTL design to the right side. And before doing or developing the test bed environment or testing the RTL design at the behavioral as well as at the hardware level, we will be performing RTL static verification in compliance with DO-254 again. So this is very important. Your RTL has to be in compliance with DO-254. So to perform that, we have a Siemens has a tool called QuestaLink, which comes with built-in rule set for DO-254, ISO 26262, and the STAR rule set. You can just load your design in this tool and produce the artifact showing that my RTL design is 100% compliant with DO-254 guideline. Secondly, when you deal with a more complex clock domain in your design, then performing clock domain process analysis is very important. This becomes very important when you go for higher levels like the level A and B. You need to produce this particular artifact of your performance of your design at the clock domain processing analysis and reset domain processing analysis. For that, Siemens EDA has Questa, RDC, and a CDC2. And when we go for level A and B, DO-254 has also mandate to perform formal analysis for your design. So one among many formal method of analyzing your RTL is RTL auto check. For that, Siemens EDA has Questa Inspect, which can perform formal verification of your RTL. Now that your RTL has been completely verified and you have the 100% confident as a designer, then we can move on to simulation and verification of code coverage, functional verification, and the hardware, your netlist verification. For that, Siemens EDA has Questa Prime, Questa 1C, Questa Prime, and in the newer nomenclature, it is called Questa 1C. So that solution is there. So this tool can perform your simulation verification at RTL level as well as netlist level. So you can see the replication of this tool. But for DO-254, well, we are performing simulation and verification. The elementary analysis of code coverage is very important. And sometimes you cannot achieve 100% code coverage because there is always a coverage gap involved in your design. So for that matter, you need to produce a formal verification evidence that the part of your code is unreachable. So unreachability analysis of formal verification for the level A and B. So for that, we have the method called code coverage acceleration using formal technology. And Siemens EDA has a solution called Questa increased coverage to help you with that. And then finally, you have to perform synthesis. Modern precision synthesis is a vendor-independent tool for FPGA synthesis. And then finally, we will move on to the placement and routing and programming the device. And we will be depending on the vendor-specific tool for that. Just for example, for your AMD FPGAs, Brigado we will be using, and for Intel FPGAs or Altera FPGAs, we will be depending on the Quartus tool. On the right side, there is a big triangle that gives the name rec tracer. So the reason why it is here is, like I have mentioned, requirement traceability is the most important thing in DO-254, and you have to have an end-to-end traceability throughout the design lifecycle, not just at the documentation level. For that matter, rec tracer is a tool to trace your requirement from your document till the verification result. So finally, this encompasses the whole of DO-254 flow and the solution that the Siemens EDA can provide you to make your life easier to produce all those lifecycle data and the artifacts required for DO-254 audits. With all this, the lifecycle data and artifacts in your hand, your project will be finishing in your time, your audits will be finishing in your time, and you can have your project or product timely in the market and beat your competitions. Finally, thank you everyone for attending my webinar session. And in the future, we are planning lots of more such sessions for DO-254. So here in this particular session, I'm giving an overview of DO-254. In the future, I'm planning to conduct a webinar session more deeper into its specific processes in DO-254. And we'll also understand what are the updates in the DO-254, like I mentioned. Now we have more clarifications of that order from FAA and the EASA, like the AMC or AC 2152A. So we'll talk more about those clarifications in those newer orders from the FAA and the EASA in the future webinar also. Stay tuned to our to our social media, in the LinkedIn, in the Instagram. We'll keep posting about updates of this webinar. And with respect to our any solutions that you want to have you want to understand more, then for inquiries, please communicate or contact to the email ID given here, islbangalore@tridenttechlabs.com. Thank you everyone again for attending my session. And I am free to take questions in the chat box now. Thank you. We haven't got any queries in our Q&A section or in the chat box. So I may have to assume that the attendees here has any question regarding the topic that we have just discussed. Okay, thank you. I have a question. So Mr. Sanjeev Copper has asked, usually DAL A and DAL B are taught in the same category. What is the exact difference between them? So in terms of criticality, the difference is there. But yeah, when we talk about the life cycle, the data that we produce for DAL level A and B, yes, Mr. Sanjeev, you are right. So they are always talk at the same category. So that same category we're talking about is purely in terms of the lifecycle data and the artifacts, and specifically the code coverage percentage that we have to produce as a part of validation and verifications. So that is the same category that we are talking about. But in terms of the sheer criticality of the actual hardware, there will always be having differences. So I may not answer the exact difference between them, but according to me, as I understood, that is the only difference that is there. Welcome and thank you for the question, actually. So any other Q&A? So we will take a few more before closing this session. Okay, thank you everyone again. So we will be closing this session since we haven't received any other more queries.